We tend to treat problem-solving as an act of alchemy, waiting for a sudden, unpredictable epiphany to clarify the path forward. But relying on a random flash of insight is an unreliable way to manage a complex system. When the moment of clarity flickers and vanishes, you are left exactly where you started. Under pressure, the default human brain searches for a similar-looking problem from the past and copies the solution. This is reasoning by analogy. The danger is that when you import a previous solution, you drag along all of its invisible baggage. You unknowingly inherit the inefficiencies and false constraints of the person who solved it before you. You end up trying to run modern, complex hardware on legacy code. Eventually, the structural integrity fractures under the pressure, and the solution collapses under the weight of its own unexamined assumptions. Breakthroughs require moving past the myth of the sudden epiphany. To reach the actual limits of efficiency, we have to treat problem-solving as a rigorous computational architecture built across 4 distinct layers. Layer 1 is the core, and it runs on a single strict axiom: first principles thinking. You stop copy-pasting from analogies, delete the assumptions, and instead recompile the problem from its absolute source. Take a look at this vertical chart breaking down the total cost of a product. When you strip away the human inefficiency, the management overhead, and the bloated supply chains, you are left with a tiny 2% sliver at the bottom. That remaining sliver is the undeniable physical cost of the raw materials. Elon Musk used this exact reduction to bypass traditional aerospace costs. Instead of accepting the standard multi-million-dollar price tag of a rocket, he priced out the raw elements: carbon, aluminum, and liquid oxygen. By reducing the vehicle to its physical constants, he isolated the exact limit of theoretical efficiency. Once you isolate those raw components, you have to connect them without creating broken dependencies. This glowing network illustrates a directed acyclic graph, or DAG. It maps the trunk of your problem, tracing the exact lineage of cause and effect so that changing one variable at the top doesn't break a critical node further down the line. When a gap appears in that logic, elite solvers use a cross-domain pipe. They find an alien industry that solved that abstract problem at scale, like borrowing Linux memory management, and pipe that pre-tested logic directly into their system. Now the core is compiled, the foundational physics are mathematically sound, but out in the messy reality of the real world, this pristine logic remains highly vulnerable. That vulnerability requires layer 2, the diagnostic. A perfect theoretical foundation means nothing unless it is aggressively stress-tested against inevitable human error. The architecture relies on stoic inversion. Instead of asking how to succeed, you ask how you would definitely fail. You list every action that would guarantee a disaster, and then you engineer the system to make those specific actions physically impossible. To spot those disasters, teams conduct a pre-mortem. Imagine time-traveling 6 months into the future to find that your project is completely dead and rotting. Starting from the assumption of absolute failure forces the brain to bypass its natural optimism bias. You look at the imaginary wreckage and trace the disaster backward, identifying the exact physical constraint or process breakdown that your team is currently ignoring. By proactively mapping these invisible failure vectors before they manifest, you build a defensive perimeter around your core logic, neutralizing the blind spots that doom most complex systems. But mere safety leads to stagnation. To escape, we need layer 3, the generative. This 3D topography grid demonstrates what experts call a local minimum, an optimal point within a very narrow field. You get trapped in the shallow valley of conventional expertise, unable to reach the massive peaks of innovation in the distance. To break out, you apply reductio ad absurdum. By pushing variables to mathematical limits, demanding zero cost or massive instant scale, the system evolves cast incremental thinking. These constraints breed technical contradictions. You might demand a machine that is fast, but also perfectly safe. To resolve this without compromise, engineers use frameworks like TRIZ. By cataloging patterns across millions of patents, TRIZ demonstrates that most technical contradictions have already been solved by someone else in an unrelated field. Deliberately breaking the conventional rules forces the logic to mutate. The result is an entirely uncontested space, a blue ocean, far removed from the flawed analogies you started with. You now have a resilient, highly innovative system. But all of that precise engineering is completely worthless with layer 4, the value. A flawless machine has no purpose unless it solves a tangible problem for a human being. We focus on the job to be done. A customer hires a product to bridge the gap between where they are and where they want to be. This is the core of the working backwards method, popularized by Amazon. Before a single line of code is written or a part is manufactured, the team writes the final press release and the customer FAQ. They define the user's exact moment of utility first. Once that utility is defined, you apply the negative space strategy. You look at the clutter of existing solutions, the extra buttons and the menus nobody uses, and you ruthlessly delete them. The true value is found in the simplicity of the void you create. To solve problems at the highest level, you cannot rely on the luck of a sudden epiphany. You must become a generalist architect, systematically compiling the physics, diagnosing the failures, and ultimately validating a high-fidelity, logically sound architecture.